I would like to welcome you all. My name is Lauren. I'm the Communications Coordinator for the National Road Research Alliance, or NRRA, and we're really glad you're here. Today we have Dr. Bora Cetin here with us from Michigan State University. It's where he currently is, and I will let him introduce the project. This is the Geotechnical project update that was voted on by all of our members to hear the update on. So I will turn it over to you, Bora.
Thank you, Lauren. Thank you for the introduction, and thank you all for being here. So this was a project funded by NRRA, National Road Research Alliance, and we completed the project last summer, finalized the final report, and it's on the web page with more details. Today I will only be able to finish summarize the research findings briefly, and what our motivation was, and what was the goal of the projects, and what we've done, and what are the brief summary of the results. So the title is kind of long, but it's basically improve material inputs into mechanistic design properties for reclaimed HMA hot mix asphalt, basic asphalt material, and recycled concrete aggregates used in roadways. I was the PI of this project, and the co-PI was Dr. Professor Edil from University of Wisconsin-Madison. And here is our research team, and we have a graduate student she completed her Master of Science degree thanks to this funding from NRRA, the Ida Gabi, and also our postdocs, Dr. Hatipoli and Dr. Choban, partially involved in this project to help us with some of the data collection and guidance of the research report that we have wrote. And of course, a technical advisor panel. Tim Anderson was a technical liaison for the Lead 4 project, and Terry Beaudry and Raul Velasquez from Minnesota Department of Transportation, and Heather Shoup from Illinois DOT, and Matt Ullman from Meta Construction provided guidance and great feedback throughout the delivery of these tasks and final report and throughout the research project. So we really appreciate their help on this project. And also, I would always like to start with the appreciation to our NRRA geotechnical team. I apologize if I missed some other members' names here, and I sincerely apologize for that. As far as I know, this is the last updated list of people in this geotechnical team, so we all appreciate your help, and I hope some of you are here, and really appreciate everybody in being here for today's presentation. And also our list of other associate members for the geotechnical team. We really appreciate your support. As you can see, we have quite a bit good number of associate members, so we look forward to your feedback after this presentation as well. And here are the friends and supportings from academia and other industry and federal agencies. I know Kevin just retired, but we also look forward to your feedback today after this presentation on this project. So what were the motivation? Motivation is really to collect, gather data about the index properties and engineering properties of these recycled concrete aggregates and recycled asphalt pavements. I assume everybody in the group knows, but what these materials are, basically these are either old failed rigid pavements, concrete pavements that are recycled, and or demolished structures that are recycled, demolished concrete structures that are recycled and are being used as a base layers for pavement systems, pavement foundation systems, or recycled asphalt pavement is an old and failed asphalt pavement services that are reclaimed is then used as a pavement foundation systems, and what their properties are in terms of index properties and engineering properties and drainage characteristics, and how they can be used as an input in the mechanistic empirical pavement design, pavement ME software and models. So overall, how the pavement ME analysis process works, there are different variety of inputs that is required to get a good payment ME prediction results when you're making your payment design. And one of these input are the material properties, including index and engineering properties and drainage characteristics. Then payment ME take all these climate, materials, traffic input, structure input into its processing and do its own mechanistic empirical analysis and predict the distress values of the materials, of the design based on the material input that you put in. And then from there it predicts based on the International Roughness Index, with these inputs, your payment will fail in 20 years, or payment will fail in 10 years. That sort of analysis payment ME provides us. So in terms of material inputs, again, in this study, we were mainly focused on the base course of the payment systems. And when it comes to that, there are a range of materials that can be used for the payment-based foundation systems. And in this particular study, the focus of the work was really on the use of recycled concrete aggregate and REP materials, recycled reclaimed asphalt pavement material, recycled asphalt pavement material to be used in payment foundation systems and what their input parameters is. So why we wanted to focus specifically on RCA and REP? I mean, there has been many studies conducted on these materials, index and engineering properties, but it was not collected in sense of a database. So in the study, that's what we tried to do. We tried to collect resilient modulus, California bearing ratio, permanent deformation angle, friction and cohesion values for these materials, along with the other index parameters that we have here. Then also, in addition to collection of all this data, including hydraulic conductivity, we tried to correlate these index parameters to the engineering properties, either strength of stiffness parameters or hydraulic conductivity parameters, to check to see if we can give a range and then you predict your resilient modulus values based on the gradation characteristic. For instance, I have few data that we can show. Instead of running MR tests, you may be able to get a average resilient modulus value that you use based on the gradation characteristics of your RCA and REP. So in the summary, the objectives basically I kind of mentioned in the motivations part, but we have two main goals. Excuse me. One of them is the actual collection of these material input data. And after we collect this material input data and we correlate these index properties with these engineering properties, and then run quite a bit payment ME analysis to check to see how sensitive these current payment ME program or models that are included are based on some of the changes, some of the differences between these index and engineering properties of RCA and REP, and how would that impact the prediction of future distresses of the payments. So data collection, we try to get data as many as NRRA states that includes this data, but also we had to collect data from other states that are not part of the current NRRA group to kind of expand and try to expand that database as much as we can with these gradation characteristics like index properties and strength stiffness properties and drainage properties. And here are the list of these parameters that we mainly focused on when we collect this data. And here is a kind of excuse me, summary of REP and RCA characteristics. And as you can see, for the REP and RCA, the lowest, for instance, lowest limit, the gravel percent was 3%, as opposed to it was 32%, approximately 32% for RCA, while the upper limit gravel for REP that we see in this database was 68.1 versus 94.2 4.1. So we collected data from almost 50, 60 papers and reports in total to really get this extensive data. And also we got the similar data for maximum dry unit weight and optimum moisture content, compaction characteristics, all other gradation characteristics, and resin modulus values, hydraulic conductivity values, and CBRs. Kind of try to get an overall sense of what we collected in this study. And then, as you remember here, if you look at here, I listed the SMR, which means the summer resin modulus value. And when we correlate these index properties with this resin modulus of the certain REP and RCA materials that are used as base material, we use summer resin modulus values, and because payment ME takes only one modulus input, if you choose to use that option as an input in your payment design. So we use summer resin modulus value, which we call as an SMR. And what SMR means, as you can, that it is basically one single point of resin modulus value for that particular material that we are interested in analyze, we are interested in using as an input in payment ME. So this is one of the graph that I took it from one of my previous study that shows in the y-axis the resin modulus values versus the corresponding bulk stress values. As you can see, and as majority of you know, I believe that resin modulus is most of the time shows a nonlinear behavior, and it is stress dependent. So depending on the bulk stresses that your aggregate materials are exposed to during this resin modulus test, and G represents granular aggregate base and RCA represents recycled kind of aggregate. So your resin modulus value of your material will change depending on the confining stress and the vertical loading stress that you apply. We call as a bulk stress the sum of the confining pressure and dynamic deviator load that you vertical load that you apply, simulating the vehicle load. So what summer resin modulus? So there are multiple different resin modulus value for your materials. And what you need is a single value to use in payment ME. And what the NCHRP 128, which is the most commonly used standard or report that is used to determine the summer resin modulus values in general, it says if you're using a material as a payment foundation value, and if you want to determine a summer resin modulus value that can be used as an input in your payment analysis, you pick the resin modulus value that corresponds to 208 kilopascal 208 kilopascal of bulk stress that resin modulus that corresponds to the 208 kilopascal bulk stress values. I apologize, this arrow shifted to the left a little bit. It should be here 208 kilopascal bulk stress that corresponds to resin modulus value is what you can use as an input in your payment ME analysis as a resin modulus value that represents that particular material as resin modulus value when it is used in payment foundation systems. So then I won't be able to, we have a lot of figures in the final report that is uploaded on the NRRA for this NRRA website for this project. We correlated these summer resin modulus values with a lot of index characteristics and did the same with the strength parameters and permanent deformation and hydraulic conductivity. But here I will mainly focus on the sum of the certain index characteristics behavior to the index characteristics to the resin modulus values. So in this figure, these are the papers that we collected the data. On the y-axis, we have their summer resin modulus values with their corresponding gravel to sand ratio. As you can see, there is no consistent trend between gravel to sand ratio of these materials versus their summer resin modulus values. Then what we do, we try to kind of put them in a different group. So if you keep as you can see, there is a wide range of the data that we collected like between maximum and minimum, but in overall the median area of the box, we have these box plots that kind of show how the resin modulus of these materials changes with the gravel to sand ratio. If the gravel to sand ratio of your material vary between 0.25 to 0.97, the summer resin modulus value that you may use is 200 megapascal based on this database. And if the gravel to sand ratio of your material is vary between 1 and 2.09, it is a little bit slightly higher, maybe 250 megapascal as an input that can be used. Of course, it's solely these are all material dependent and stress conditions dependent. So under this bulk stress condition, and with the database that we get, this is the input value that you can use as an input summer resin modulus data for your pavement ME analysis for recycled asphalt pavement material. And we did the same for the RCA material. And in that case, the variety of the resin modulus values for RCA materials with the change in the gravel to sand ratio at the higher range is much wider, while it is a little bit, the box plot is a little bit smaller compared to higher gravel to sand ratios. And in this case, what this study says, the summer resin modulus of the RCA materials in the medium value can be estimated as 180 megapascal for any range of gravel to sand ratios. Of course, especially at the higher gravel to sand ratios, more data may need to be collected. One of the reasons why we have high variety in the summer resin modulus values, SMR versus gravel to sand ratio data, we have a less amount of data, and it provides high variability. And we did the similar things with the D60 value from the gradation characteristics and try to correlate that with the summer resin modulus values SMR of the REP materials. Again, you may not be able to see consistent trend. Again, we try to divide them in groups at different ranges. And here, basically, if your D60 value within this range, you can assume as a median range, your summer resin modulus is 180 megapascal for REP materials, versus if the D60 value of your REP is within this range. This is the wide range that you can use, but on the median value, close to 250 megapascal, resin modulus value may be used as an input in your pavement ME analysis if your D60 value is in this range. And similar comparison that we did for the recycled concrete aggregate for D60 versus SMR values. And in this case, it clearly shows that the lower the D60 value for RCA tend to have higher summer resin modulus values than those with higher D60 values. And again, the D60 value, if it is in this range, it is higher than 200, it's around 210, 220 megapascal, while it is 170, 180 megapascal resin modulus value if the D60 value is in this range for RCA materials based on the database that we collected. So if we get to this general, like I said, we have compared these, do these comparisons for all many variety of different gradation characteristics between gradation characteristics and the drainage and hydro engineering properties. I only show a few examples. So the general trends that we see and what lessons we learned from this data collection, the general trends that we see in recycled asphalt pavements, the higher D30, D60, and the gravel to sand ratio and coefficient uniformity resulted in higher resin modulus values. I didn't show the graphs here, but higher fines content didn't seem to affect the resin modulus of the REP materials when they are used in pavement foundations. So, of course, as expected, OMC here represents the optimum moisture content. The higher optimum moisture content, as expected, resulted in lower resin modulus values. And the temperature was an issue with the recycled asphalt pavement materials. And with the higher temperatures, of course, because of the still asphalt binders exist in these materials, higher temperatures resulted in lower resin modulus values, unless there are some thermal preloadings. That the University of Wisconsin, Dr. Riddle conducted some study. If you compact your rep materials under higher temperatures, it has better resistance to the other temperature changes in time. However, in the field, this is not much applicable, but in the lab stage, it showed that thermal preloading may be useful to improve the temperature change resistance of these rep materials. And higher D10 value resulted in higher hydraulic conductivity for rep materials. And higher fines content, as expected, resulted in lower hydraulic conductivity. And again, the higher rep contents resulted in higher resin modulus value and lower CBR, which was contradicting with each other. And lower higher rep content required lower optimum moisture content of the materials, which is expected because asphalt binder is hydrophobic material, so higher rep content would result in lower optimum moisture contents in these materials. And as expected, high rep content increased the permanent strain, permanent deformation potential of these materials. Excuse me. So what lessons we learned and what were the general trends that we observed with the recycled concrete aggregate materials? The higher gravel to sand ratio and coefficient uniformity resulted in higher resin modulus values for RCAs. And as expected, higher fines content resulted in lower resin modulus values. And higher maximum dry density unit weight, of course, which means higher compaction, it basically resulted in increasing the resin modulus of these SMR values of these RCAs as expected. And as expected, as with all granular bound or unbound materials, as we observed, the higher optimum moisture content resulted in lower resin modulus values. And then if we next four rows, how the RCA contact impacted the hydraulic conductivity, compaction characteristics, and permanent deformation of these materials. So, of course, higher RCA content caused lower hydraulic conductivity and lower maximum dry unit weight and higher optimum moisture content of the materials, because when you mix these RCAs with regular granular aggregate bases. And as expected, unlike rep materials, an increase in temperature didn't seem to impact the resin modulus of the RCA materials because there is no asphalt binder in these RCA materials. So it was not surprising to see a higher temperature didn't impact the resin modulus of these RCAs. And overall, the observation, though, what we observed, which we didn't have it as clear with the rep materials, overall the resin modulus of RCAs were higher than the virgin aggregates, like the ones that we collect from quarries, the regular aggregates, conventional aggregates, resin modulus values. Then what we did, we get this data collection and wanted to do some sensitivity analysis in pavement ME software. And as I mentioned in the beginning of our presentation, this is the pavement ME requires several inputs. The hourly climate data is one of the input which we use the mnroad climate data, or the location that is embedded in the pavement ME software that represents the mnroad conditions. And material collection, which the data that we collected is used and varied in this study. We used the mnroad location as an input. And we kept the pavement structure constant and traffic conditions vary depending on the sensitivity analysis that we do, and we payment ME calculates the following payment performance parameters. However, since our focus was really, we only changed the material characteristics for the payment foundation systems like RCAs and REPs used in the analysis. So we focus, for instance, on asphalt only on the IRA and rutting, and with the concrete IRA and transverse cracking. So the general inputs that we use that stayed constant throughout the analysis, we designed it for 20 years, and climate data we picked it for Minnesota mnroad location. We kept the groundwater depth 10 feet, and here are some of the flexible payment asphalt layer input and rigid payment concrete layer input. And these are the traffic inputs that we have that we have used to simulate the low traffic, medium traffic, and high traffic. These are the traffic inputs that we used, and we vary the base thicknesses and for flexible payment depending on these traffic values, both for flexible and rigid payments. And here are the distresses again with the for the rigid payment ME analysis. We mainly focus on the IRI and joint faulting, and for the asphalt layer, since we're focusing on the base, we really focused on the terminal IRI, again International Roughness Index, and total payment routing values, and these are the target values and reliability values that we picked. So we varied the input parameters. We kind of varied quite all these are the varied input parameters for the recycled base aggregates that we used, and we varied the resin modulus, and the following gradation characteristics and hydraulic conductivity value, and then we calculate the payment performance again both for flexible and rigid payments. And in the flexible payments, since we only vary the recycled base parameters, we thought IRI and total routing would be the main things that would be impacted. And with rigid payments, we focus on the IRI and joint faulting. So here are how we look into this impact of resin modulus on payment performances. The top table look into the inputs for REP, and the below table shows inputs for RCA layers. So then we use the median data for across the data that we collected. So whatever the median resin modulus value that we get, we collect the gravel percent, medium. We get the median gravel percent that corresponds to this data. And then with the lowest resin modulus value, we picked for instance, the lowest resin modulus value was 24,000 PSI value. So we found that data, we found that report or paper that reported this lowest resin modulus value, SMR value for this for that particular material. So we picked that gravel percent that from that paper or report that reported this lowest resin modulus value, and used that as an input. Same with the highest materials, and same with the we did the same thing throughout the entire sensitivity analysis when we determined the lowest and highest materials, materials with lowest and highest resin modulus values. And then we varied the traffic conditions as we described in the previous tables, and we compared the IRI values. The figure on the top left corner shows the impact of course, traffic load. With an increase in traffic load, of course, you see an increase in IRI across all graphs. So I won't touch base as much on the traffic load impact, since it wasn't really the main focus of the study. But how does the IRI values impacted by the SMR values. When we look at the figure here, of course, the one that has the lowest resonance modulus value, the rep that has the lowest resonance modulus value had higher IRIs, and with an increase in the resonance modulus value, as expected, we see a slight decrease in the IRI value. And similar trend kind of was observed, even though it was less impacted with the RCA materials, or with the figure on the bottom left corner. And if you look at the total routing with both our rep and RCA graphs on the right hand side of the slide, the total routing decreases with an increase in resonance modulus values of the materials. So this is as expected. And another thing that shows, even with the lowest resonance modulus values, when you use these reps and RCAs with the input parameters that we used for other structured layers of the payments, they don't exceed the IRI limits. The dashed line here shows the IRI limits and total running limits. So these materials seem to be safe to use with these inputs in payment ME analysis. On the other hand, when we get to the rigid payment performances at the high traffic conditions and sometimes with the medium traffic conditions, I mean, with the high traffic conditions, we see a lot of early failures in terms of IRI and main joint faulting when we use these resonance modulus values for these payment stress conditions. In the low traffic conditions, there is no problem. And overall, what we see with an increase in resonance modulus value, we see slight decrease in the slight decrease in the IRI performances under any traffic conditions, but it's not as impacting as it was observed with the flexible payment performances for both materials. And another set of, like I said in the report, we show much more refined payment ME analysis, and I will show another set of figures that we show the impacts of fines content on payment performances. Again, the same idea. We use the median fines content value and SMR values that across the table here for rep and RCA, and then for the lowest and highest, we find the report that reported the lowest fines content, and then we find that paper, which is Allen et al. 2010, and get what was the gravel percent for that rep, and it was 3%, 97%, and its SMR value was 39,000 psi. So we put the input that was provided for this Allen et al. 2010, and we for the highest for the rep material that reported the highest fines content was Camargo et al. 2003. So we collect all this the data from the Camargo et al. 2003 that corresponds to this highest rep content. And same thing was done for the RCA material. And again, we look into the payment distress predictions, and with an increase in fines content, regardless of the traffic conditions and payment distresses, an increase in fines content cause an increase in the IRI and total routing values as expected. And again, even at higher traffic conditions, though, with all these materials at this wide range of high fines content, the system did not fail in terms of IRI or total routing under these payment structural conditions and the data that we use for rep and RCA materials. And on the other hand, the story changes again with the rigid payments, that with an increase in fines content, actually we see some decrease with the IRI content with the reps, while we didn't see that much that change with the RCA with an increase in fines content, especially at high traffic conditions. IRI even increased more. And for the mean joint faulting, we seem to again the REB material and with higher fines seem to perform a little bit, I mean, not noticeable, but somewhat at high traffic condition, improved the joint faulting distresses a little bit, decreased the joint faulting distresses a little bit, but still it exceeds the mean joint faulting values considerably at high and medium traffic conditions. So same with the RCA material. With the RCA material, with an increase in fines content, we didn't see significant changes except from lowest fines to medium fines in terms of mean joint faulting. So fines content didn't seem to be very impactful of RCAs in terms of mean joint faulting. So overall, with this payment analysis, I think rigid payment portion of the analysis should be studied more. I mean, with the new updated payment ME, I think there are more improvements to the rigid payments and rigid payment distress modeling. So these things may need to be revisited. But I think based on, I didn't show all this data, but in the report we provided all in detail. Resin modulus value of these recycled base layers the recycled aggregate base layers are the most influential, and we didn't observe any relationship between the 10 values and their payment performances. And with the flexible payment design, there is a significant relationship between the gradation characteristics of these REB materials, both REB and RCA materials, and their resin modulus values. And as expected, higher traffic values cause more damage. And higher fines content, like I said, we had for flexible payments, we were clear. With higher fines content, it ends up lower resin modulus value, and with lower sand content, which resulted in higher total rotting. And higher fine in flexible payments and higher fines content resulted in higher IRI in recycled aggregate base of flexible payments. And in rigid payments, again, like I showed, all cases with these recycled aggregate bases represent recycled aggregate base as a voice cost material in low traffic volume satisfied the minimum required IRI and mean joint faulting distresses, but with medium and higher traffic, the results were inconclusive. Here, I think what we would recommend really to determine the gradations and summary resin modulus of recycled aggregate base materials. But with this database, if you don't have the capacity or time to do MR value, by just determining the gradation characteristics, you may be able to predict the resin modulus values. And again, rigid payment results were not really conclusive. Yes, we see we saw results there that exceeds the limits, but there are more things going on that side. So that's why we would recommend more sensitivity analysis to be conducted on these rigid payment results. And overall, in terms of implementation, the database is created. It's also in report and also provided as a very well organized Excel file, so anybody can use that database for their payment design and analysis. And I think this is the really most important slide. We really thank to National Road Research Alliance for sponsoring this project. And thanks to technical liaison Tim Anderson and other technical advisor panel members, Terry Baudry, Raul Velasquez, Matt Ullman, and Heather Shub. And also thanks to my research group and Dr. Tans Riddle from University of Wisconsin-Madison. And having said that, this is the end of my presentation. I hope it was brief and clear. I'll look forward to your feedback and questions.
Thank you so much, Bora. I don't see any questions in the chat, but if you have any questions to any of our audience members, looks like Eob has a question. Feel free to unmute yourself.
Good morning. Thank you, Bora, for the excellent presentation.
Thank you.
I have one question. So the IRI that you are showing, they are simulated values, not actual values, right?
Yes, they are simulated values, not actual values. You're right.
Okay, so one of the things that we've been seeing from different studies, including some from ours, what we see is that when you have payments that have like base foundation which have cement content or high cement content, they do tend to kind of be stiffer in winter and then lead to crack heaving or something or tainting that affects IRI. So if you drive on those roads, the first thing that you will notice is they have a very bad ride quality.
Okay.
Do you think that this mechanistic simulation is capturing that, or is it diminishing that?
I would say the current model that we use not fully covering that because this was the I think the last version. It is somewhat covering it, but not fully. I think it needs more improvement to that. Yeah, the freeze-thaw effect on the RCA materials. I don't think it has a model that kind of like this payment ME has a model that varies these resin modules values with that freeze-thaw conditions. But I don't think it takes this cement content into effect as we would like to see, as it is really happening in the field.
Because the first thing that they affect, which we see, is the IRI, the ride quality.
Yes, and we see it slightly, right, but not as it is in the field, in my opinion. So the current model, I don't think, especially when it comes to this cement-rich RCA materials or cement-treated bases, does not really fully incorporate that in the modeling and prediction as we see it in the field.
Thank you, Bora.
Yeah, thank you.
Any other questions or comments? Oh, I just saw something in the chat. It looks like a response from Derek Tompkins for EAB. MEPDG pavement ME calculation for IRI is effectively summarizes distress by pavement type, accounting for specific field behaviors associated with reclaimed materials would ultimately be a local calibration, which is tricky.
Yeah. Thank you, Derek. Any other questions?
All right, well, thank you so much for joining us. Thank you to Bora for the presentation. Next month, on January 18th, we will be hearing from the ICT team on understanding and improving pavement milling operations. And then in February, we have the preventative maintenance team project update on spray-on rejuvenator test sections. And then we actually have marches lined up, but I don't have enough details to share quite yet. But thank you so much for being with us again today, and have a great holiday weekend, holiday week ahead, and we will see you in 2022.
Thank you very much all for being here, and provides an NRRA again providing the support for this research project. I hope it was useful to everybody. Thank you for being here.
Absolutely. Thank you.